Hey there, dear learners, and welcome back to the Lesson BCE channel. Today, we are diving headfirst into galaxies and dark matter. We're going to be venturing into some of the most magnificent structures in the entire cosmos, and honestly, looking into one of the absolute greatest unsolved mysteries in modern physics. Before we start uncovering the secrets of the universe, do me a quick favor, hit that subscribe button and like this explainer. All right, let's jump right in by laying out our learning objectives. By the end of this explainer, you'll be able to define a galaxy and identify its components, distinguish between the different types, describe our Milky Way, explain galaxy clusters and superclusters, and really understand the basic evidence for dark matter.
So, part 1. What exactly is a galaxy?
You know, when we look up at the night sky, it's pretty easy to think of space as just this giant, empty void with a few isolated stars sprinkled in. But that is actually not the case at all. A galaxy is this incredibly huge, highly organized collection of stars, gas, dust, planets, and a bunch of other celestial objects, and it's all held tightly together by the relentless pull of gravity. And when I say huge, I literally mean mind-bogglingly huge. Just one single galaxy can contain billions or even trillions of individual stars. Now, if we were to unpack a galaxy to see what's inside, we'd obviously find those stars we just talked about. But we'd also find these vast clouds of gas and dust, called nebulae, which are actually where new stars are born. Plus, there are star clusters, and right at the center of most galaxies, a supermassive black hole that kind of anchors the whole system. But hey, take a really close look at that second-to-last item on our list, dark matter. I want you to tuck that away in your mind for now, because it's going to become the central, massive plot twist of today's explainer.
Okay, moving right along to part 2, types of galaxies.
Galaxies generally fall into 3 main visual categories. First up, we've got spiral galaxies. These guys have a flat, rotating disk with really distinct spiral arms, and they are absolutely packed with gas and dust, making them super active nurseries for star formation. Next, we have elliptical galaxies. These look more like a round or oval smudge in space. They contain mostly older stars, and because they have very little gas and dust, star formation is basically stopped. And finally, irregular galaxies. Just like the name suggests, they don't have any regular shape. They're often the chaotic leftovers of 2 massive galaxies colliding. It's actually really cool. The physical shape of a galaxy instantly tells us this whole story about its age, its history, and exactly what kind of stars are living inside it.
Which brings us to part 3, the Milky Way. Let's zoom in on our own cosmic home.
When we map out the structure of the Milky Way, you can clearly spot the central bulge, the flat galactic disk, and this huge, expansive halo surrounding the whole thing. And check out where our sun is located. We aren't sitting right in the center. We're actually hanging out in one of the spiral arms, the Orion arm to be specific. And yep, we are orbiting a supermassive black hole dead at the galactic center called Sagittarius A star. All right, part 4, galaxy clusters and superclusters. Let's zoom back out.
Gravity scales up in a pretty spectacular way. You see, galaxies aren't just out there flying solo. Our Milky Way is gravitationally bound to a neighborhood of over 50 other galaxies, forming what we call the local group. But wait, it doesn't stop there. These groups of galaxies are pulled together into absolutely massive, sprawling structures called superclusters. It basically forms this giant cosmic web of visible matter that stretches across the entire observable universe.
Now for the fun part, part 5, Introduction to Dark Matter.
So, we've established the ground rules of the cosmos, right? But here's where astrophysicists encounter a glaring mathematical mystery. When they point their telescopes at spiral galaxies and study their rotation curves, which, by the way, is just a fancy term for measuring how fast stars are moving at different distances from the center, something just doesn't add up. Why are the outer stars moving so incredibly fast?
Let's break down what we expect to happen. According to good old Newtonian gravity, the orbital velocity squared equals the gravitational constant g times the mass inside the orbit m divided by the distance from the center r. Since almost all the visible light, and therefore supposedly all the mass, is concentrated right in the dense center of a galaxy, the stars that are farther away from that center should orbit way more slowly as their distance increases. But here's the kicker. There is a massive, undeniable contrast between what our math predicts and what we actually observe. Our calculated expectation shows the speed dropping off smoothly as you move outward. But the actual measured velocity of those stars, it goes up and stays completely flat. Those outer stars are whipping around the galactic center way faster than they should be.
Honestly, by all the laws of physics, if the visible matter was the only thing there, the galaxy should literally rip itself apart and fling those outer stars right into deep space.
So what's holding it all together? Since visible matter alone absolutely cannot explain this gravitational effect, scientists came to a wild conclusion. Galaxies must be completely wrapped in massive, invisible halos. We call this dark matter. It's a completely invisible form of matter that doesn't emit, absorb, or reflect light at all. It is totally undetectable to our standard telescopes. Literally, the only reason we know it exists is because of the immense gravitational pull it exerts on the stars we can actually see.
Let's put some numbers to this in Part 6, Calculating the Unseen.
Let's actually test this with some math to see just how much mass is hiding out there. Say we observe a star at the outer edge of a galaxy. It's orbiting at a blisteringly fast 200 kilometers per second, and it's sitting an immense 5 times 10 to the 20th power meters away from the center. If we rearrange our gravity equation to solve for the total mass m, we plug in that velocity, multiply it by the distance, and divide by the gravitational constant. The result? Roughly 3 times 10 to the 41st power kilograms. That is an astronomically huge number. When we compare that to the mass of the stars we can actually see, well, there's a massive shortfall. This calculation brilliantly proves that galaxies contain vast, unseen amounts of material keeping everything locked perfectly in place.
Okay, time to test your understanding with a quick practice question. Why do galaxy rotation curves provide evidence for dark matter? Is it A, galaxies have no gravity? B, outer stars move faster than expected? C, stars stop moving? Or D, dark matter emits light? Go ahead, pause the explainer, think about the flat rotation data we just looked at, and drop your answer down in the comments below. I'll be checking to see who gets it right.
To wrap up today's explainer, let's hit our key takeaways. Galaxies are colossal systems bound together by gravity. They mainly come in 3 types: spiral, elliptical, and irregular. Our very own Milky Way is a classic spiral. Also remember that galaxies don't stand alone. They clump into giant clusters and superclusters. And finally, the flat rotation curves of these galaxies give us undeniable proof that dark matter, an invisible, mysterious mass, is out there holding the universe together.
Thank you so much for learning with Lesson BCE today. I want to leave you with this final thought to ponder. If the data shows us that the vast majority of the mass shaping our entire universe is completely invisible to our eyes, what other incredible cosmic secrets are we entirely blind to, just waiting out there in the dark to be discovered? Keep that curiosity alive, keep looking up, and I'll catch you in the next experiment.